Okay. All right, so we'll be recording this, and then I'll go back to sharing the screen. Good. Oh, there we go. Now you can watch this. All right, now how is this going to work? I'm going to have to somehow minimize this.
Just move it to the back. Just click on the other tab.
Oh, okay. Yeah, there we go. So, you got it. Okay, so my little green light is on. I told you the first day of school, please be patient with me as I fumble through this. And so I do appreciate the help that you give me. And hopefully I have two or three tennis players that are out there doing regionals right now, and they're the ones that asked me to record. So we want to give them our best shot. So anyway, we're talking about writing the net ionic equation. We have this first reaction. And what I suggest that you do is just write out for yourself what are the ions that are present. So we have barium ions and chloride. And then we have sodium and carbonate. So among this set of four ions, using this set of solubility rules, is there a combination present that you would expect to form a precipitate? Yes, and why?
I failed that test, bro.
No, bro. It's something different. Look at number 6 down here. Sulfides, carbonates, chromates, and phosphates are generally insoluble with everything except for the group 1 ions. So yeah, that is right. It's barium ion and carbonate ion are going to make a precipitate. The sodium is going to be soluble with everything. That's rule number 2. Chloride is soluble with almost everything. That's rule number 3. There's 3 exceptions to the chlorine solubility, and none of them are up here. So yeah, it's going to be the barium and the carbonate. So the question is, figure out what precipitate would be made and write the balanced net ionic equation. So that is like that. Now the next thing, the next one that we have, anybody have any questions about that first one? That's what we do. Use those solubility rules. I'll flash those every time that we have one that we need to determine is there a precipitate made. So in the second one, a solution of potassium hydroxide is added to a solution of iron 3 bromide. Okay, so we have potassium ions, hydroxide ions, iron 3 ions, and bromide ions. Is there a combination of ions here that will make a precipitate? Using the solubility rules. And tell me which rule you're using. What do you think? Emma, what do you think? It is rule 5. The K, though, K started as a dissolved solution. We started with a solution of potassium hydroxide. It is rule 5 that we use, but rule 5 says hydroxides, slightly soluble means they're going to make precipitates. But it says the soluble hydroxides are sodium and potassium hydroxide. Those are actually soluble. That's not going to be our precipitate. So almost all hydroxides are going to make a precipitate. It's the hydroxide with the iron that's going to be, and we're looking for an insoluble one, not a soluble one, an insoluble combination. So yeah, whenever you have hydroxide present, first of all, make sure it's not an acid-base reaction, because the next type of reaction is going to have hydrogen compounds and hydroxide compounds to neutralize each other. But when you see that there's no acid in it, then think precipitation of the hydroxide, because hydroxide, almost everything will precipitate hydroxide, except for the group 1 compound. So the net ionic equation for that one would be iron plus 3 hydroxides yields FeOH taken 3 times like that. Make sure you have the parentheses on there. And as simple as the net ionic equation is, make sure that it's balanced still. I put the 3 there just naturally. Other hours I would leave the 3 off and say, okay, is this complete? And wait for somebody to say, it's not balanced. But yeah, make sure that your net ionic equations are always balanced. Even if it doesn't say, like at the top of the slide there, it didn't use the word balanced. It just said, give the net ionic. But the implication is you always balance your equations. All right, we good with that? Let's try the next one. I'll go on to the next slide. So the next one has solutions of ammonium nitrate and calcium chloride are mixed. Get rid of all this. Ammonium ion, nitrate ion, and calcium ion and chloride ion. Is there a combination of ions in this set that will make a precipitate? Good. I like what I'm hearing, which is nothing. What do you think? Ammonium chloride? Ammonium compounds are always soluble. So ammonium with anything won't make a precipitate. This is the one Richard was asking about this earlier. Hey, is it possible for us to have no reaction? Yeah, this is an example when there is no precipitate that's made. And that can happen. There is a box on this one. It says, write the net ionic equation. I give you a nice box for that. What do you write in there? If there is no reaction, just put no reaction. Or N/R, meaning no reaction. So yeah, that's possible. This one doesn't. So ammonium doesn't precipitate anything, and nitrate doesn't precipitate anything. So yeah, no matter what these two things are, they won't give a solid. Okay, last one here. Aqueous lithium chloride is mixed with aqueous mercury 1 nitrate. So we have lithium ions, which is a group 1 ion, and chloride. Mercury 1. Mercury 1, remember, is this oddball, Hg2 with a positive 2. And then nitrate ion, NO3 negative. So is there a combination of ions in this set that will make a precipitate? What do you think? You got it? Yes. What rule? It is rule 3, yeah. Chlorides are generally soluble with everything. They're very soluble, except for if you have mercury, lead, silver. And sure enough, we have the mercury. And by the way, it is only mercury 1. There's a mercury 2 that is actually soluble with chloride. It's just mercury 1, which is a bummer. It's too bad that not all mercuries are insoluble, so we didn't have to try to keep those straight. But yeah, so this ion and this ion will make a precipitate, because mercury is one of those exceptions with the chloride. The net ionic equation, you're not going to like the chemical formula. It is Hg2 with a positive 2. There's our mercury 1 ions, polyatomic. And then we have the chloride ion, yields the formula of the product, Hg2Cl2. I don't like this myself. I wish I could reduce it. Doesn't look right to me. But we've got to keep those polyatomic ion formulas sacred. We don't ever mess with them or alter them at all. So if I cut that down to HgCl, that is not reflecting the actual chemical formula. This is not balanced. Don't forget to balance it. We need a 2 in front of that term, and then it'll be balanced. Now, regarding the chlorides, rule number 3, chloride, and I told you this yesterday, chlorides are so common. They're abundant in the earth, so there's a lot of reactions that happen with chloride. It's a very useful element in chemistry. So chlorides show up a lot. Bromide, iodide, not as much. They're common, but not like chloride. Chloride is one of the most used elements. So I just mentioned this, and you may have been scrolling through the notes and you see this, Major League Soccer, what's that? I use this as a memory trick. Troy is such a soccer town. If you grew up in Troy, I'm pretty sure that you played soccer at some point in your life. I've never seen any community sport like I have soccer in Troy.
Why can't we win a World Cup then?
I know. And why doesn't Troy and Athens win the state title every year in soccer, both boys and girls? I don't know. Seems like you should. You're always good, but and some years, I think it was 2013 was the last time girls won the state. But anyway, MLS, Major League Soccer, this is for you if you follow soccer. I can't watch professional soccer. I don't like it when they take their dives, and writhe on the ground. No, it's not for me. So anyway, yeah, Major League Soccer, these are your 3 elements that are insoluble with chloride: mercury, lead, silver. So if you can maybe use this as a memory aid, think Major League Soccer when you're trying to think of the exceptions to the chloride solubility. That's what that's doing there. Now, we're not going to spend any time with this. We had a reading assignment about molarity. I will mention the dilution formula. We have to use the dilution formula a lot here, really all year. We'll use it a lot in this chapter, and then we won't use it for a while, but then we'll use it a lot later in the year too. So that dilution formula is very handy to us. Be ready to use it. Now, then we get to this. This will be where we end for the day with this one problem. We have half of our class still, and we'll just do this one problem. Now, I'm going to switch over. I'm going to use the iPad for this part because there will be some things I want to write on this. There it is. Okay, good. So yeah, there's our example. Oh, I love this too. Number 61. There's not many words that I would find beautiful in chemistry, but here's one of them that I do find to be beautiful, and I really am serious. The word aliquot. Isn't that a nice word? An aliquot. You don't ever use that. I mean, you could go up to, if somebody's serving at McDonald's or whatever. Hey, I need an aliquot of Coke, and that's a thing. But nobody uses that word. Aliquot is a word that means a measured sample. So we have and this is right from our book. So yeah, they're being kind of elegant in their language. 100 milliliter aliquot of 0.2 molar sodium hydroxide is mixed with 100 milliliters of 0.2 molar iron 2 chloride. So we have 2 solutions with 2 different things that are dissolved. They get mixed together, so you have this combination now of 4 ions. And is there a reaction that occurs? And if so, write the balanced equation. So I'm going to get rid of this. I guess I could just write it on here. I'll do that. So we have sodium ions, hydroxide ions, iron 2, and chloride. What do you think is going to be our precipitate? The iron with the hydroxide. Yep. These 2 are going to precipitate. And so now it doesn't say the net ionic in this case. It says write the balanced equation. So we'll write the whole thing. So it's NaOH plus FeCl2 yields FeOH taken twice. Now I'm going to write it wrong at first. I want to write it wrong to let you know that I don't have much patience for rookie mistakes in this class. I don't want you to still act like a Chem 1 student anymore. We're well into the course now. If you write that the other product is NaCl2, I'm not going to appreciate it. Now, why would you put NaCl2? What do we have here? We have iron leaving the chloride and going with the hydroxide, and then the Na leaving the hydroxide and going with the chloride. Now look, I have one Na in this formula and two Cl, so everybody wants to put NaCl2. Why is that wrong? Why, Daniel?
They're not balanced.
The charges aren't balanced. Yeah. Do you see why somebody would put a 2 there? Yeah, because there's a 2 after the Cl there. So FeCl2, I would just change to NaCl2. Yeah. Rookie mistake. Not good. Really, the iron and the chloride, as you know, are not together. They're not a compound anymore. This is an aqueous solution. You have iron ions present and chloride ions present. They're not together. There was 2 chlorides for every iron, but yeah, when the sodium and the chloride combine, they do have to have the right balance of charges. So it's just NaCl. Now this is not a balanced equation. We've got to balance it, and that's why, you know that there's 2 chlorides over there. You want to account for the 2 chlorides over there, but you account for the 2 chlorides with a coefficient like that. And then we have 2 Na's, meaning we need 2 Na's over there. 2 hydroxides matches. We'll put those. Okay, so there's our part A, right, the balanced equation. And now we get to stoichiometry. What mass of the precipitate forms? Now we know which one is the precipitate. So we can come over here and say, okay, we're going to try to figure out what the mass of that is. You're given the amount of both reactants in this reaction. You have the volume and molarity of both. Now, I won't do this every time. In fact, this is probably the only time I will do this, but just so we're clear on what to do with the information we're given, remember that molarity is moles of solute divided by liters of solution. And I need the number of moles of each of the 2 reactants so that I can figure out which one is the limiting reactant and then determine the amount of product. So we're given the molarity of both solutions. We're given the volume of both solutions. So you'll use that to find moles. This is very common among these problems. You'll very often be given molarity and volume so that you need to find the number of moles. So moles would be the molarity times the volume. Just rearranging this thing, get moles by itself, that means multiply out the volume of it. Volume's got to be in liters, because that's what the definition of molarity is. So that means that the moles of NaOH would be the molarity, 0.2, times the volume, which is 100 ml, changes to liters, like that. I wanted to write it out one time, just so that you would see it. From now on, when you have molarity and volume, just write out the number of moles. Multiply them, write out the number of moles. You do that so often you won't even think about it. So yeah, the moles are 0.0200. I'm going to try to stay consistent with the sig figs, because I know that many are sig fig insecure. So over here in my chemical equation, just figured out the number of moles of sodium hydroxide, so I'm going to put 0.0200 moles. Do you notice that we had the same volume of both solutions and the same molarity of both solutions, so you'll have the same number of moles of both reacting things. Which one is the limiting reactant? Do you remember how to find limiting reactant? Get into moles of both, divide by the coefficient. We already have moles, so just take that divided by its coefficient. That becomes 0.01. That divided by its coefficient is 0.02. And then to use the lowest one is the limiting reactant. That would be the sodium hydroxide. Yes? So easy to find limiting reactant that way. That way we don't have to say, okay, 0.02 to that, 0.02 to that, whatever one's left. We'll just do that very quickly. So I'm going to make this very noticeable. My limiting reagent is the NaOH. So that's what I'm going to use to determine how much product is made. And let's see, I'll just do this on the bottom of the slide. 0.02 moles of NaOH. Go from moles of that to moles of that. It's 1 to 2 ratio. 1 mole of FeOH taken twice for every 2 moles of NaOH. And then we do need grams. It does ask us what mass of precipitate forms, so that one last step. Iron hydroxide, we have hydroxide is 17 with the O and the H, times 2 is 34. 34 plus 55.8. 55 plus 34 is 89. And then we have a 0.8 there from the iron. So, yeah, there's our setup. We can do this without a calculator too. You can see that we have 0.02 divided by 2 makes 0.01. 0.01. And then times 89.8. Multiply that by 0.01, you just move the decimal over 2 places. So the mass of the precipitate is 0.898 grams. All the students from last year are so resentful of you being able to use a calculator on the tests. Until this year, every time I mean, for the entire history of the AP exam, people have not been able to use a calculator on the multiple choice part until this year. So you're the first group. It was so weird for me in the stoichiometry test a couple days ago to watch you using a calculator during the multiple choice. I've never given that before. Not one time have I seen anybody using a calculator, unless they were a rogue and they were using it when they shouldn't have been. Yeah?
So if they didn't have calculators, did you give them nicer numbers? Or?
Yeah, they were number friendly. Yeah, yeah. They were. But yeah, I mean, people got hung up on the mental math that they had to do. It really didn't cause their scores to be any lower. Because they would look back at their test, they would be like, oh, I couldn't do the mental math, but then they were able to do that. That was not what they had trouble with. Oops, I didn't mean to do that, sorry. But yeah, they wish they could have used a calculator like you can now. So anyway, yeah, we have the mass of the precipitate. Now the last one. Question D. D stands for dreadful. This is this one is dreadful. So I'm going to do this one over here on the board. The question is, I'll erase this work so we can really see what's going on. Question D. What is the concentration of each of the 4 ions when the reaction is over? What is the concentration of 4 ions when the reaction is over? We're going to get 4 different answers. We need to have a concentration of sodium, of hydroxide, of iron, and of chloride. So we have to do those 4 individually. Keep in mind this is after the reaction. I'll tell you why I'm trying to make that very clear in a moment. So we'll need the concentration of sodium, concentration of hydroxide, concentration of iron, and the concentration of chloride. Now, you know what the concentration is, well, how it's defined. It's the moles of sodium. Notice, we're looking for the concentration after the reaction's over. So we need the concentration of sodium ion that remains after any reaction happens, divided by the liters of the solution at the end. Trying to make this very systematic and clear. So we're going to do that for all 4 of our ions. The concentration of hydroxide is the moles of hydroxide that remain. divided by the liters of the solution at the end. Same thing for the iron. Moles of Fe that remain, I'll just put REM for remaining, I'm tired of writing all that. Divided by the liters of the solution at the end. And then the percent of chlorine, or the molarity of chlorine, moles of Cl negative remaining. Divided by liters of solution. Okay, let's try this. The sodium. Oh, before we do the moles, let's talk about that denominator. What is the denominator for all four of these? It's going to be the same because all of the ions are in the same solution after it's combined. What is that volume? I have 100 milliliters of sodium hydroxide and 100 milliliters of iron chloride, and I combine the two together. What is my final volume? 200 mLs, which is 0.2 liters. All four of these will have the same denominator. They're all in the 200 liters or milliliters of solution. Now, I want you to remember that this gets to be a confusing point. Anytime you need a concentration after a reaction, you've got to combine the volumes of the two things that you mix together. So watch out for that. And I'll remind you of that. But yeah, anytime you combine solutions, get the final volume. And that's what volume you'll need. All right, so we already know our denominators, we just have to worry about the numerators. So it's going to be 0.2000 liters in my denominator all the time. How much sodium ion remains? Well, how would you classify sodium in this reaction? What is sodium in this reaction? Well, it's part of the limiting reactant, but the sodium ion itself.
Wait, for the safe, it would be 0.2000, which would be 0.20,
My volumes both went to the 10th place of a milliliter, which would be, I got 4 sig figs, so I need to keep 4 sig figs for my volumes. That's what I did there. Okay. Sodium. Yes, sodium is part of the limiting reagent. Yes? Sodium is a spectator ion. Yep. What does it mean to be a spectator ion? Nothing happens to it. It's not involved in the reaction. How much sodium did I start with? How many moles? You had the right idea. You said it wrong. You said 0.2, didn't you? It's 0.02. You said 0.0. What you said 0.2. Yeah, so it's 0.02 mole. When you have 0.02 moles of this compound, you got 0.02 moles of sodium, and you have 0.02 moles of hydroxide. So the sodium ion started at 0.02 moles, and none of it got used. We didn't add any sodium to it. So it was 0.0200 moles minus 0 moles got used. So my final number of moles of sodium is 0.02. Divide that by the total volume, which was 0.2. So therefore, my concentration of sodium would be 0.02 divided by 0.2. 0.100 molarity of sodium. For the hydroxide, now the hydroxide was involved in the reaction, so that one is going to be not quite the same as the sodium. How many moles of hydroxide did we start with? 0.02, same as the sodium. There's one of each of them in that compound. So we started with 0.02 moles minus how much of the hydroxide ion reacted? All of it. How do you know all of it? It was the limiting reactant. The definition of limiting reactant is it's the reactant that gets used up. It all ran out. So we don't really need to know much more about the hydroxide. That's good enough because if I started with 0.02 and all of it got used, that means I used all 0.02 moles And therefore I have 0 left. Doesn't matter what my denominator is for that one. I get the big goose egg for the hydroxide ion because it was the limiting reactant. Now I'm going to do one thing here. I'm going to just, so for your sake, if you want to look back at this and see how you did it, keep in mind we know that the hydroxide was the limiting reactant. Therefore, we found the limiting reactant back when we were finding part C. So yeah, that allows me to know that all of the hydroxide. Now where is the hydroxide? The hydroxide is all on the bottom of the container, tied up with in a solid with the iron, making this solid precipitate. There is no more hydroxide ion floating around in the solution. Is it present in the container? Yeah, it's still there, but it's tied up as a solid now, and I'm talking about concentrations of ion remaining in the solution. There is no more hydroxide ion in the solution. You see that? Okay, let's go on to the other one, the iron. I would say the iron is the worst one to try to figure out its concentration. Why is the iron the worst one? Because the iron is involved in the reaction, but it's not the limiting. So we have to figure out how much of it got used. We have to do stoichiometry just for that one. All right, so how many moles of iron did we start with? 0.02. Somebody said 2 zeros in there, but it is point.
0.0.
Okay, good. So we started with 0.02 moles. How much of the iron reacted?
0.1.
It was 0.01. How do you know that?
I calculated
How did you calculate it?
using like the limiting reaction.
That's right. Yeah. If you want to know how much of the excess reactant, you all had this on your test in the last chapter, how much of the excess reactant remains. What do? You start with the limiting reactant. It's 0.02 moles of NaOH. I know all that reacted. So multiply by how many moles of what the mole ratio is between these two. It's 1 mole of FeCl2 for every 2 moles of NaOH. That's it. 0.02 divided by 2 is 0.01 moles of FeOH taken twice, not FeOH, sorry, FeCl2 got used. I know all that reacted because that was the limiting. That means that amount, I didn't round to sig figs. I'm more interested in the concept right now than the sig fig mechanics. If it really bothers you, there. Okay, so that's how much got used. I started with 0.02, I used 0.01. So over here, that's the calculation that I'm doing. How much iron is still floating around in this solution? It's not all used up. I started with 0.02 moles, I used up 0.01 moles, that's what that calculation just told me. So 0.02 minus 0.01 is my numerator. And then divided by that 0.2 liters. So one thing I like about this problem is that all 4 of the ions are going to wind up with different concentrations at the end. So we can see how that's not always the case. Sometimes you'll have multiple ions that have the same concentration. They're all different in this one. So 0.01 is my numerator, divided by 0.2 gives me 0.05 molarity of iron. So yeah, some of the iron got used up, so it makes sense that I'll have a low concentration of iron compared to the others. All right, that one was a tough one. And then the chloride is another spectator, so that's an easier one. I like the spectators. You don't have to do much with them. But take a look at the chloride over here in this term. How much chloride did I start with in this reaction? Not 0.02, 0.04. Because there's 2 chlorides in every FeCl2. So if I have 1 mole of FeCl2, I'll have 2 moles of chloride. And if I have 0.02 moles of this compound, I'll have 0.04 moles of chloride. So that's my numerator, is I've got 0.04 moles to start with, minus however much got used, which is 0, it's a spectator. And that's it, then divided by the volume. This one is 0.04 divided by 0.2, which is 0.2 molarity. So take a look at what we've just done. We came up with, at the end of this reaction, there's 0.2 molarity of chloride, twice as much as sodium ion. Both of them were spectators. Why is there more of one spectator than another? Well, it's because we started with more chloride ion. We started with twice as much at the beginning. We still have twice as much because they didn't get used. The hydroxide is all gone. It's 0 because it was the limiting reactant. The iron is lower than it would have been because some of it got used. That's how we do those. Now, I do have 2 different hours today. People ask the question, some of you might have the same question. Why did I multiply by 2 Cl's in that one, but I didn't multiply by 2 NAs over here because there's a 2 there as a coefficient? Don't I have to multiply by 2 because there's 2 coefficient? No, you don't. A coefficient is very different from a subscript in a formula. The coefficient does not mean that I doubled the amount of sodium and hydroxide. The 2 coefficient is there to tell me what ratio these 2 things react in. This gets used twice as fast as that gets used. That's what that 2 is doing there. When I start with 0.02 moles, because I put a 2 there does not suddenly mean that I double my amount of sodium hydroxide. It just means that that reacts twice as much as that does. The 2 there next to the chlorine means that I'm going to have twice as many ions of chlorine as I have iron. So, yeah, be careful. The subscripts and the coefficients are not telling you the same thing. Oh, almost time to go. Can I answer any other questions about this or give you a replay on anything? I will ask you to digest this. We'll do another example of this tomorrow. Rishi?
Wait, so this is just like a general question.
Okay.
So the Na and Cl are combined together in the final solution?
Well, it looks like it is like here, NaCl, but it is aqueous. So it's just sodium ions and chloride ions dispersed.
But you still put them together in the...
In the chemical equation we do, yeah. Like if I evaporated all the water, I would get sodium chloride. But I'd also, there would be some iron ions left. I'd get some iron chloride as well because some of the iron didn't precipitate. So yeah, you write it like this. Now, I think I told you yesterday, this is not very descriptive because the sodium and chloride really are not together. They're dispersed on their own. Both of them surrounded by water. Tomorrow, we'll do an example. Look how similar this example tomorrow is. You're going to have volume and molarity of 2 different reactants, just like we did today. Give the balanced ionic equation, so we'll go through and figure out which one runs out first. Find the mass to precipitate, just like we did here. And then part C, C for dreadful. But this one isn't as dreadful, that's why it starts with C. Find the concentration, not of all 4 ions, but just of the excess ion that reacted after the reaction happened. So yeah, we'll get a little bit more practice figuring out what is the concentration after the precipitation. I think that's it for today. I'm going to turn off my recording. Hope it was helpful, guys.